for I think some tours at Voltabox, some presentations previously through the years, and very nice to be back with you all again, and a real pleasure to see some friendly faces. So tonight we're going to have a discussion which every time I speak to the IEEE, I'm not really quite sure where to start, because you guys, as everyone knows, are way smarter than me, because I'm a mechanical engineer. You guys, the electrical engineers, are way out ahead of the average here. So some of these things I'm going to discuss, I'm quite sure will be very pedestrian for you. Hopefully there are some things which are new and different and interesting, but the discussion is battery energy technology. The legal bits, these are my opinions, not the opinion of my employer. So battery energy storage systems, I'm going to use the acronym BESS quite a bit through the evening. It's known by other names as well: renewable energy storage systems, energy storage systems. But this is, as I hope to explain over the next hour, why battery energy storage is the nexus of all energy, with the subtitle of why the coal, oil, gas, automotive, trucking, taxi, rail, shipping, utility industries are about to become unrecognizable. In our lifetimes, these industries will become unrecognizable from what they are today. Now, it turns out I've got a friend whose family is in the oil change business. And it occurred to me that every corner gas station, oil change, joint transmission shop, auto mechanic business, convenience store, grocery store, hotel, mall, restaurant, electrician, job seeker, Uber driver, and investor should really pay careful attention to these extraordinary megatrends that are going on that we're going to discuss tonight. And oh, by the way, this is the biggest opportunity for business that I believe we will ever see in our lifetimes. Part of the reason I say that is because we've been here. I've been working in clean tech for many years, decades, and it has always felt like this. It has always felt like we are really working hard to turn a battleship. But today, I feel rather differently. I believe that we are right here. And I believe that in very, very short order, we will start to see major changes. If someone could go on mute, that would be appreciated. So this graphic, if you've never seen this before, in my opinion, this is one of the most interesting and compelling and important single-page graphics I've ever had the time to invest in and look at this. I used to have it printed out on an e-size drawing on the wall in my office. This represents all of the energy in the United States. And on the left side, all of the incoming energy sources. The middle shows where that energy goes. And then on the right, we have energy services, productive, useful energy. Upper left is rejected energy. Every engineer in the crowd should be cringing at that upper right-hand quadrant, the rejected energy, because that is an awfully inefficient system. And in fact, there's good news to be had here regarding this. If you are interested in this graphic, and trust me, you can spend days, weeks, and months just studying this, thinking about this, and considering this within your own business interests. If you're in energy, just search on Lawrence Livermore National Laboratories flow, or LLNL flow, and you will come out to here. So this graphic, we'll come back to this over and over again as we peel away the layers of the onion here. But notably, this is 2019, and it's 100 quads. A quad is a quadrillion BTUs. And there's the conversion to 1 kilowatt hour down below if you want that. The 100 quads is just sort of a fact of where we are, just awfully convenient, though, that everything is very easily laid out in terms of percentages of the entire United States energy. So on the left side, we're going to look at some of these primary energy sources. Petroleum, 36.7% of US energy in 2019, coal, natural gas, wind and solar we're going to spend a little bit of time on, and then interject the storage element into this. So if we think about energy and storage and energy, they're highly intertwined, perhaps in ways that you might not have thought about before. So I'm going to submit for your consideration some of the incumbent energy sources. In this case, the dispatchable energy sources, so biomass. The sun comes out, it shines on the ground, a tree grows up, we process that tree after it has stored that solar energy.
Yeah, I guess I got on.
Okay, Mike, could you go to mute, please? And you have a renewable energy source. You could say the same thing about coal. Solar energy comes down, makes plants, long time goes by, that energy gets stored in coal, and then you have a thermal process and you have usable energy. Mike, would you go on mute, please? Kai, could you mute everyone, perhaps except for me? So we can apply the same consideration to oil. Solar energy comes down, plants grow, dinosaurs eat them, hang out for a couple million years, you get oil, it makes a wonderful storage medium, and then you have a thermal process and you get usable energy out. Say the same thing here, similar here, slightly different, but similar. I'm going to posit this for your consideration. Different kind of solar energy in this case, but all heavy metals come from the sun somewhere, from some star. And so I'm going to posit that. And then we have solar thermal. So this is a much more direct, time scale here. Solar energy comes in, it goes into solar thermal storage, and then gets turned in a thermal process into usable energy. And then you have these guys, which are not dispatchable. So wind and solar, again, solar energy going to usable energy this time. Notably, there is no storage here. So let's talk about storage. One of the oldest is pumped hydro, in which case we take energy, we pump water uphill, that becomes its own storage, and then it flows back downhill, making usable energy. Kinetic energy, flywheels, for example, you put energy in, store it as kinetic energy, take it back out again. Thermal, put energy in, store it, and then take it back out again. Compressed air energy storage, same. Battery energy storage, same. Hydrogen, which is a very interesting discussion unto itself. You put energy in, it stores that energy, and then it comes back out. Similar with supercaps. Geothermal is slightly different because the ground serves essentially as the storage. You don't need to put energy in on the first order anyway to get usable energy out. So today, my discussion is going to be going from this, coal, gas, etc., solar energy storage, usable energy, to this, solar energy storage and usable energy. It's really important that we have now added this into the mix, because the wind and the solar by themselves lack what all of the rest of those incumbent energy sources provide automatically, is the built-in storage capability. But today we have that. So let's look at them a little bit individually. So the future of coal, it is purely a matter of economics. If you have any opinions red or blue, red, white, or blue, or other, it kind of doesn't matter. This is simply a discussion of economics. So today, the profitability of coal power in the United States, there's 254. Kai, can you see my mouse on your screen? Am I able to convey information to you? Can you see that on your side?
I can see it.
Yes.
Okay, very good. Thank you, Bob. Okay, so the U.S. coal fleet, and this, everything in here obviously it has a date to it, and it changes on a daily basis, quite literally. There's almost certainly less total operating capacity in the U.S. today than this number, but 22% of that fleet runs cash flow negative. That's obviously pretty important from a business perspective. Let's go look at China. China has about 4 times as much operating capacity online. Almost 60% of it is cash flow negative today. They're building, planned and under construction, a significant adder to their capacity, also about 60% uneconomical right off the bat. In Europe, a little bit smaller coal capacity today, 62% negative cash flow, and not they do have 8 gigawatts planned and under construction. In the US, you'll note that we have 0 plants under construction. If we parse this down a little bit deeper and look at the United States, go down to Texas, that's the Texas grid, ERCOT, TRE, we are 38% uneconomical, meaning that 38% of our coal-fired production loses money every kilowatt hour that they produce. The average profitability is $3 per megawatt hour. If you go up to the northeast, the Northeast Power Coordinating Council, NPCC, 100% of their coal-fired generation loses money at the tune of negative $31 per megawatt hour every megawatt hour that they produce. So you can look across the US and you get a sense of where things are in terms of the coal. If you come closer to Texas, this is borne out in the facts that these coal plants have closed in 2018, and they continue to close through 2019, 2020, and into today. So back to our Lawrence Livermore energy consumption. Since you can see my mouse now, this big, heavy black line, 10% of all US energy goes into electricity generation. And over time, and that time scale is accelerating considerably, this black line is going to go down to 0. Let's look at oil. Are we at the sunset of oil as we know it? I'm going to submit that the answer is yes. So there is a site called Carbon Tracker. It tracks many different facets of this, and they have some really wonderful graphics. This has to do with peak demand. So let's come out and look at peak demand for coal was reached in 2013. That was the peak of the coal production, the demand for coal. It has declined since then. Internal combustion engine cars, ICE is an acronym we'll use here. Internal combustion engine cars reached a peak in 2017. It is being posited by Carbon Tracker that fossil fuels reached a peak in 2019. And if in fact you go to the Lawrence Livermore National Labs energy graph for 2020, you will see a major decline in oil, but we had a pandemic, so that's not fair. And I'm not using those numbers in my discussion, but they're readily available. I've got them here if we want to discuss them in the Q&A later on. So if it is true that fossil fuels reached peak demand in 2019, then you start to see this, peak demand leading to stranded assets. So if it is in fact true that petroleum reached peak demand, The incumbent expectations are always optimistic, and they project along this line. Whereas the incumbent actual sales start to decline by definition if peak demand has been met. That leaves these stranded assets out here, and that is being caused by the challengers, which we'll, of course, dig into shortly. So how do we gauge this against real life? Well, all of the oil majors have stranded assets on the order of $8 billion that Total in France wrote down, 17 billion that BP wrote down, 22 billion that Shell wrote down, and shale companies writing off $38 billion, and Deloitte predicting at least $300 billion in stranded assets to be written down. So oil companies, not me, but oil companies start to wonder, is it worth looking for oil anymore? If you remember on that peak demand graph a few slides back, exploration and production reached a peak some years ago. So BP said that it would no longer do any new exploration in new countries. In fact, they said they were evaluating their portfolio and they had proven oil reserves going to leave them undeveloped. Canadian oil sands are even at graver risk because they are much more expensive to extract and to process into refined products. So no new oil sands projects fit into the world according to today's ground rules. And over on the shale side, hundreds of bankruptcies are being reported. BP sets the tone here, setting out a strategy for a decade of delivery towards a net zero ambition. And I think this is really important because we will continue to need oil. We just won't continue to need it on the part of the graph that puts it into your engine any longer. So back to our energy graph. Petroleum, 36.7% of all US energy, 26% going into transportation. My day job is to help move this down to zero. And this is already being seen in terms of the electrification of transportation. So this line is going to go towards zero, and this line here will come down and feed the transportation sector. What about natural gas? Well, you hear a lot about natural gas being a bridge fuel, natural gas being clean. Even the terms cooking with gas and the term natural gas. These are marketing terms of art of the industry. They have served them well. And about a year and a half ago, they realized that this push to electrify everything would sooner or later come back to natural gas. And so there was this push toward renewable natural gas. And so if you've been past a landfill recently, you'll have an example of renewable natural gas. Well, a couple of weeks ago, the industry got really upset when California started to ban new natural gas installations in new construction. So your natural gas stove in your home in California is at risk for any new construction. And not to be outdone, the Texas legislature moved to kill the gas ban proposed by the city of Austin. So if we look at natural gas now, natural gas goes a lot of places. It's a very important fuel in our mix. 12% of our national energy budget goes into electricity generation from natural gas. And then you have substantive contributions to residential, which would be your water heating, space heating, and cooking. Same thing with commercial, similar to industrial, but also down here, you have a lot of thermal industrial processes. So those natural gas bans are going to start to diminish these lines, and they're going to move them towards zero. This will diminish the industrial processes. I anticipate will carry on for a long time. Over here, interestingly, this 0.98, this is natural gas going into transportation. You can interpret that as fuel cells, fuel cell vehicles. So this line up here, 11.7%, technically, you all understand that's 11.7 quads out of 100 quads here. So that's going to continue for some time. And I don't expect that to change in the very near future, but it will change. And we can count on that. And I'm gonna pause just for a second here because I had expected some other information. Nope. Okay. So moving now into the future, moving from oil to wind, and with wind, solar. To understand the importance of these and where these fit, again, going back to economics. Did I lose my screen sharing? I think I did. Apologies. Okay, Bob, am I back? Or do you see my screen with the
now you're back.
Theodore Paul Wright? Okay, all right, very good. Thank you. This fellow, Theodore Paul Wright, he is the inventor of Wright's law. You may have heard of the learning curve. You may have heard of economies of scale. The term that he used was learning rate, and he used it to calculate the factors affecting the cost of airplanes at the Curtiss Wright Corporation. And he reckoned that each doubling of production yields a 10 to 15% improvement in efficiency. That improvement can go to cost reductions or greater profits. So his work is extremely important. And one of the somewhat famous analyses of this was an analysis of the Model T, the average list price now. And you can see each doubling of production allowed a declining price curve, and that followed along the 10 to 15% that Wright's law predicted. Well, we can take a leap from 1903 all the way out here to 2012 for Ford costs, but in this case, we don't have Model Ts anymore, but we're using this dollars per horsepower metric. And you can see that even over more than a century, Wright's law holds. Now, interestingly, some of you, I'm sure, are familiar with Cathie Wood, famous investor today, her company ARK Investment. She has done a lot of work using Wright's law, applying it to mature technologies, famously Tesla, hence her investments in Tesla, as she used Wright's law to project the declining cost curve of the Tesla vehicle, and was able to say at a certain point, he's going to start to become profitable. He's going to start to increase profits. He makes a good investment. When I say he, you all know who I'm speaking of. And so she famously was a very committed investor in Tesla, and it is Wright's law that got her there. If we take that same thinking and we apply this over on the solar energy side, all of these in the top right, these represent different projections, different groups, Lazard, Lawrence Berkeley National Lab, International Energy Agency, all of these guys have taken historical learning rates and they have applied them out into the future to predict utility scale solar pricing. Interestingly, all of them were wrong. They were way too pessimistic. Even though they used learning rates in the 30 to 40% and Wright only projected 10 to 15%, the actual costs came in much lower, much faster than what was predicted. And so what this translates to is the pure economics of the energy business. And Photovoltaics magazine in May of 2020, a year ago, predicted sunny places could see average solar with prices of 1 to 2 cents per kilowatt hour in 15 years. And I would be willing to bet real money they're too pessimistic. So when you take these elements and you put them together into the cost of a solar panel, and if you look at the blue on the left, $100 back in 1975, when I was taking classes on solar energy, I remembered $100 per watt, which is a crazy lot of money. Today, well, according to this graph, it says 61 cents. In reality, there may be people on this call who know better than I. The last I saw it, it was about 35 cents per watt. Okay, so that translates to well in excess of a 99% cost decrease in this energy source. As you decrease that source, the installations go up, and you can see the exponential growth of the solar installations. So let's go get some hard facts on this. Let's look at Texas energy generation. Here's 2010. I tried to get 2015, but ERCOT didn't provide it, and the biomass is not my doing. That's a fixed graphic. And here is 2020. So let's take a look at the coal. Here's coal, 2010, 40%. Here's coal, 2016 now, 29%. And here's coal in 2020 at 18%. So it is less than half of what it was 10 years ago, and it is on a steep decline curve. If we look at natural gas, we all know natural gas has gone up as far as its contributions, 38, 37, actually that's down, and then up here to 40. And if we look at wind, 7.8%, doubling 5 years later to 15, and another 50% increase again to 23%. And this number will continue to rise in Texas, as will this number, which at 2% here is barely recognizable, barely even makes the chart here at all in 2016, and it didn't make the chart in 2010. So what we are starting to see in the Texas grid is that solar energy has finally reached a point where the costs of installing a system have become competitive with our very low-priced natural gas, and is able to be competitive. And as noted earlier, Wright's law predicts that those costs will continue to go down, and I have every confidence that they will. So the future of energy is in storage. If we think about storage, you may think about batteries, and you may think about this guy right here. That would be fair, and most people in my business at Voltabox, we use Tesla as a reference because everybody, I was going to say understands Tesla, but I'm going to not say that, because in fact, everybody does not understand Tesla, and I'll explain that more as we go on. But in addition to the Tesla, you should be thinking about this. And so for me, in my business and my world, I divide these two things up into the entire world of energy. On the left, we have the energy that is mobile. On the right, we have the energy which is static or stationary. You would call that the grid. If we think about storage, there's all kinds of storage. Battery energy storage is just one element of many different kinds of energy storage. And within Battery energy storage, you have many different kinds of battery. There are flow batteries, lead acid batteries, sodium batteries, lithium ion batteries listed here, and there are many, many more. And inside of lithium ion battery, you have many, many, many different options and variables, permutations, if you will. So this slide is entitled, "Don't Fight the Standard." And that's a rule I have come to live by. Don't fight the standard. And lithium ion batteries are the standard. How do we know that? Well, back in 2013, you could see there was a reasonable mix of different types of energy storage. 2014 started to consolidate some of those. 2015, considerably more. And then there were breakthroughs in the lithium ion battery space, 2016, 17, and 18. Now it is to the point where the lithium ion battery is the unquestioned, undeniable leader in its space. And part of that goes to the cost element. And that cost, again, goes back to Wright's law and the economies of scale. I may need to let the dog out here in a moment. We'll see. Let's discuss lithium ion cells. There, again, all manner of permutations, the chemistry, the capacity of the cell, the formats of the cell. So here is one cell format. Now, you may not be aware that all of these manifestations of energy storage, battery energy storage systems, a lot of them are made of these guys. That battery is a lot like the battery you'd put into your flashlight. It's different, but it's very similar. And you might have tens of thousands of these in your Tesla. So it is, at the end of the day, very simple. You take what the industry calls a cell, that is a cell, a cylindrical cell, and you gang them in series and parallel to come out with whatever electrical properties are needed for your system. And they come in different formats. So these are prismatic cells. These are called pouch cells. Each one of these is different in numerous parameters. Size, weight, volume, energy storage, cost factors, and such. But these are the three primary elements that I use on a daily basis in my business. Now we take those cells, we put them together into the Lego building blocks, the modules. These become the building elements of any battery energy storage system 99% of the time, without getting into too much subtlety here. Within this, I know the text is small. Perhaps you can see up at the top left here is a nickel manganese cobalt cell, 24 volt. And this is a standard thermal package. Here's an air-cooled package, and here's a liquid-cooled package, okay? Here is an NMC 48 volt, and this is a pouch module. This is a very large module. You've got smaller modules for cylindrical cells, round cells. You've got different chemistries, a lithium titanate oxide and a lithium iron phosphate. Those would be common cell chemistries amongst many in the battery energy storage world. So we'll take those modules, these are slides from Voltabox, and we'll take those modules, we'll build them into systems. And those systems will come in many different sizes, shapes, configurations, capacities, and apparently colors as well. And they will go to their very purpose-built applications. And here is exactly where those batteries will go to. So buses, underground mining, fork trucks, agricultural equipment, etc. So this, in my world, I work more in smaller volume, higher mix product development applications like we just saw. But the big revolution, the important driver for so much of this is the automobile, okay? And so there are 4 generations here of battery packs for automobiles here. And you can see just looking at them, you know, they appear to change considerably as time goes on. And of course they do, they get much safer, much less costly, higher specific energy, higher energy density, and represent a greater value to the end customers, which in this case, Volkswagen, GM, BYD, who makes buses, and Tesla. So you can see the progression of the industry. We are essentially here now at the 2nd generation, okay? I don't know that BYD is actually doing this on a commercially available basis right now. Possibly, I'm not aware. And this is a conceptual design from Tesla where you'll work to reduce the cost by removing a lot of the materials, and you will go from the cell directly to the chassis. This is a new concept in the industry. And you can see if you take the cell and you remove all of this packaging and integration part of the bill of material and try to reduce that down to its absolute essence, which is the cell, then you can again continue to reduce costs. Wright's law drives this discussion of a gigafactory, and many of you have seen this very famous image of Tesla's gigafactory out in Nevada. That is up and running and in full production now. And you may have been wowed by the word gigafactory, but you may not have known that a gigafactory is not rare. It's not unusual. In fact, in this graphic of Europe, 600 gigawatt hours of annual production from many different providers. And I'd like to draw your attention up here to Northvolt. These guys are interesting to me because they have located themselves, I believe, above the Arctic Circle. And part of the reason they've done that is because they are using renewable energy. Scandinavia has a lot of hydroelectric power, and they are taking advantage of that to make an extremely green battery pack. They also have built into it from the very beginning recycling. People oftentimes ask about recycling. And so today, I work with companies in the recycling business who can recycle well in excess of 90%. Northvolt will quote you 90%. Other companies will quote you higher reclaim rates toward the higher 90s as far as reclaiming that metal and reusing it again and creating your circular economy. So this is just one graphic of gigafactories around the world. Certainly in Asia, there's a whole lot more, but this one is Europe. Oh, wait a minute, there's nothing showing in Spain, and all by itself, there you go. That's Spain's interest in battery technology development. All of this feeds directly into the algorithm developed in Wright's law. So as a result, we get these economies of scale. On the left side, you can see the price of a lithium-ion battery pack in 2018 dollars in this case, and you can see that declining cost curve. On the right, it's a little bit more graphical with some projections out into the future. 2024, at an 18% learning rate. Again, learning rates we've seen can be considerably higher than that. But at an 18% learning rate, they're projecting a $94 per kilowatt hour implied price in 2024. Why is that important? Because the $100 per kilowatt hour just happens to be the industry metric where we consider that the vehicle will be on par with an internal combustion engine. And as soon as the industry reaches the point of parity with an internal combustion engine, everything in the world of transportation will flip upside down. People go to buy a car and they look at the sticker price, they look at their monthly payment, they look at what is it going to cost them. They do not look at what is the operating cost, because they just don't think that far. But when they realize that the purchase price is less than the ICE vehicle, and oh, by the way, an educated salesperson can explain that the operating expenses are much less, then you have an entirely new business in the transportation world. So the future of energy is in lithium-ion batteries. There's significant advantages over alternative batteries. Lithium made up 95% of stationary energy storage. Prices have dropped over 85% since 2010 and continue to drop quite precipitously. Manufacturing capacity continues to expand at a torrid pace, as we showed. You can expect continued price drops. And this manufacturing capacity can reach into terawatt hour range shortly here. And these data are not the latest. The latest data would be even more optimistic beyond that. So given all of the above, and perhaps you perceived some optimism on my part, there are challenges, okay? And the cost today is the primary challenge, okay? When you are considering an electric vehicle or a battery electric vehicle or a plug-in hybrid electric vehicle versus an internal combustion engine, the electric vehicle still costs more. And that's if you are just looking at the capital expense up front versus the operating expense. The EV already beats the ICE. I'm going to move it along a little bit faster, Kai, just to let you know so that we have some time for Q&A. I think about 7:15, 7:20, I'm supposed to finish up. So there is obviously ongoing cell cost reduction due to Wright's law, the economies of scale, but there is also the kilowatt hour component. The industry is increasing this specific energy, the watt hours per kilogram, and that is increasing perhaps, that's an important word right there, faster than the cost reductions. So within the public, range and range anxiety is a concern. The way you fix that is you increase the amount of energy on board and you increase access to charger networks. The battery life, the replacement. My brother, when I bought my Chevy Volt 8 years ago, he said, now, Tom, you need to make sure you get rid of that car before you hit the 8-year warranty. And that has been in my mind ever since. And now that car is 8 years old. So that's a concern. How do you fix that? Well, there's a lot of work going into cycle life improvements on these cells. And you may have heard discussion of a 1,000,000-mile battery. There are several companies around the world who are talking about and have made claims to a 1,000,000-mile battery. So that's one way to solve some of this concern on the part of the consumer. Charge time is, in my opinion, one of the real issues here. This is a concern. And, if you're going to have to, as my wife puts it, I don't want to have to eat that much pie to wait every 200 miles for the car to charge up again. So that's a real issue. That's being addressed by specific power, improving C rates, and the ability to charge in about 10 minutes. And then you have this one, what the industry euphemistically calls thermal events. Feel free to call them fires if you insist, but there are a lot of safety improvements that are coming, including electrolytes, which are a primary source of the catalysis of the fires. So technology advancements, there is a tremendous amount here. And I won't go through these in detail, but there are so many technology advances. And I know there was one woman who was interested in this. We can certainly dig into any one of these items, but I'll briefly go through these. So nickel, manganese, cobalt, those numbers refer to the portions of nickel, manganese, and cobalt in the cell. And the 955 refers to 9 parts nickel, half a part manganese, half a part cobalt. Then you have inorganic electrolytes, which will remove the organic electrolyte, a source of thermal events. You have different technologies right here in Austin. Dr. Buddy Mullins at the University of Texas developing a new type of electrode. Dr. John Goodenough, inventor of the lithium ion cell, along with several other colleagues around the world, has developed a solid state battery, one of the most important near-term and future elements within the industry. And there are different solid state technologies which are being developed now in many different quarters. Amorphous lithium anodes out of our Idaho National Lab, single crystal electrodes. I observed within the solar world the difference in polycrystalline and monocrystalline wafers and the differences that you would see. And so you're weighing the efficiencies on one case versus the reduced cost on the other. And there's business models to be made in both cases there. Recently, Tesla announced a tabless design. Interestingly, this is not a new idea. Right here in town, and in fact, right within your IEEE consultants network, you have representatives from Rolled Ribbon Battery Company, and their basic design is a tabless design. Tesla is very good at the marketing and got a lot of buzz about this, but Rolled Ribbon had this, in fact, some years earlier and has intellectual property claims against this. But what that does is it allows for a better thermal management, and it allows for a higher C rate, better delivery of power. There are other ones, dry battery electrodes, coatings, different formats, polymer cells, hybrid lithium metal, ceramic separators. And if you look down at the bottom, lithium ion today, the specific energy is about 250 watt hours per kilogram, but lithium itself is good for 12,000. That should be 12,000, not, there should be one more zero in there. And so you can see the potential, right? That's important. So when we look at the idea of all energy, we look at two different parts, the mobility part and the stationary part. The mobility part, everybody thinks about automobiles, trucking, buses, delivery vans, drones. These all exist today. It's good, it's wonderful. Agriculture is picking this up. Skateboards now, you see kids on skateboards. Mining is where Voltabox works. There are Harley-Davidson electric motorcycles. I'm not sure how they get that noise out of them, but they have electric motorcycles. Electric bicycles have become quite a big deal. Municipal applications like street sweepers, for example, marine applications. Some of you have written on the Maid of the Mist at Niagara Falls. Probably when you wrote on it, it was a stinky old diesel engine. If you wrote on it today, though, it would be a pristine, clean and quiet battery-powered ferry. Battery power in marine applications is really starting to take off, especially for short haul, like ferries, for example, but also for medium haul marine applications. Military applications. Military is very interested in all of this. Aviation. You actually have electric aircraft, commercial electric aircraft, good for short haul. And this is starting to become part of the public awareness. And then personal aviation. There's a company here in Austin making a personal aircraft that you can take and go fly to work in. Stationary and the microsecond monitoring and millisecond response of those lithium ion cells is important here. You guys know that better than I do in the IEEE. So utility scale energy, of course, behind the meter storage at your residence, at your commercial business, even your industrial business, that's all part of the world of stationary. But you also have panel level storage, solar panels that would come with storage built into them. And all of this allows for distributed energy resources, residential, utility, and And then the many facets, this idea that batteries are essentially all things to all people in the utility industry, because they serve as both a source and a load. So they can provide voltage support, frequency control, feeder line support for transmission and distribution avoidance. They can address reactive power and load following, energy imbalance, provide distributed generation for risk mitigation, variable generation smoothing, and they can provide time shifting in the case of, for example, the very famous California duck curve. So these two worlds, the stationary world and the e-mobility world, what's important, it's really important, if you take anything away from this discussion, is the future happens right there at the intersection of those two worlds. So today, this future is based upon a vehicle-to-grid technology and an architecture. This requires a vehicle which is bilateral, a bilateral capable vehicle. So my Chevy Volt and your old Tesla are not bilateral capable. Well, let me take a sidebar. As far as we know, your Tesla is not bilateral capable, although there is plenty of rumors and buzz about the ability to flip a bit over the air and to change your car into a bilateral capable vehicle. That's actually really, really important here. You need a bilateral capable charger. My charger in my garage goes essentially in one direction. I take power from my solar system, I put it out to the grid connects to my car battery gets charged. With vehicle to grid, I would need a charger that runs in both directions. And then you need the software to communicate and to manage this transaction. Well, vehicle to grid, you could have vehicle to building, you could have vehicle to home. During the Snowmageddon back a few months ago when we were all iced in, I was really kicking myself that I did not have an energy storage capability here at the house to be able to take advantage of my solar system to run my house, to run the motor for the heater, and the natural gas was available. I could have heated my home and could have had a few lights on to be able to keep the family safe and warm and comfortable. If I had a vehicle to grid, vehicle to home configuration, I could have been able to do that successfully and avoid an unpleasant several days. There's also vehicle to vehicle, and if you take all of those things together, the industry calls this V2X, so vehicle to anything else. And then if you take those, if you have all of them together, you're able to talk bilaterally between your home, your car, the grid, your home energy storage system, your vehicle energy storage system, the grid. You now have the potential to create a virtual power plant, and then you can monetize that with a virtual power purchase agreement. So this is not something way out in the future. Today, here in Southeast Austin, Whisper Valley, that's a picture of it, has all these homes with geothermal and solar systems. And you can add your Nissan Leaf, which has bilateral charging capability today, add some home energy storage, and you can, and in fact, they have built a virtual power plant here in Austin. Now, big surprise, Tesla has done the same thing, okay? So this auto bidder platform that they have ties all of their infrastructure, all of their rooftop solar, all of their car batteries, all of their utility scale power packs and mega packs, puts them together, has a software overarching software control of this, and is able to then deliver a virtual power plant Now, here's a couple of numbers. If you start to look at the 100 kilowatt hour battery packs in larger cars like Teslas and many others, and you start to run the math on how much energy storage is in those cars, what you'll find very quickly is that there is more energy storage available than the entire United States nuclear power plant fleet. Okay. And that's not exactly a fair comparison because that nuclear plant will run for, I think, about 18 months before it needs to be refueled, whereas that Tesla, if it's got 100 kilowatt hours to give up, it could be done in an hour. But I think that you see the potential value in this as you have these distributed energy resources scattered across all of Texas, all of the United States, all of the world. And in fact, this is up and running today in Australia. And I believe, I'm not sure if it's Tesla, but there's another virtual power plant in the United Kingdom. So we come back to this. And we move into questions and answers. So I don't know how you want to do that, Kai. Do you want to read out, or people just want to, shout out their questions?
Yeah, either way. Let's. Louis, are you taking note of all the questions? Or Clyde?
Actually, there's not that many questions. There's just a lot of comments.
Okay.
I'm seeing the chat box.
And let's just open up the floor, and everybody who's questioned, then unmute yourself and ask the question directly.
Yeah, some people already have the questions in the chat. And again, some of us would like to ask questions if it is okay.
Of course.
Oh, just a simple question. I think the energy density, when you want to increase it, of course, it will take care of the volume. But I see you have the weight per unit. That's consideration. I would like to know if there's any consideration on the life of this shelf life versus the operation life of these energy storage sources.
Yes, yes, there is. In fact, if you receive a specification data sheet for a lithium-ion cell, it frequently will include elements associated with storage. And that will include details of what the storage temperature should be, what the storage state of charge of the cell should be, and how often you would need to go back and recharge it. So there is an entire protocol for that. It is a meaningful element. These cells do discharge. There is a self-discharge element. There's a lot of variables that contribute to that, including what is the starting state of charge at storage and what is the temperature at the storage site. But an easy rule of thumb is they lose 2 to 3% per month. And that's much less than some other cell chemistries and cell technologies. But it is a real issue, and you do need to account for it. And we do provide storage and maintenance guidance with our products, and that's a common and standard thing. Other questions?
Reason that I just asked because IEEE provides some of those cells. I mean, the storage things, and then I had it, and when my last visit somewhere outside Houston, I went and I found that that was already, it was dead while I had charged it here. So it was sitting there, and I was just concerned that if there is something that is happening, and we have to have that consideration. Okay, thank you.
Tom, from Bill, question is, can battery-driven transportation vehicle bring down the heat signature in the future?
Can it bring down the heat signature? Is this a greenhouse gas question? Well, let me state, if I assume that the question is, will electric vehicles bring down the heat signature in the climate? The answer is no. What they will do, however, is to contribute to a solution so we don't continue to add to the heat signature. But even if we went to a zero carbon economy, a zero carbon world today, we still have all of that CO2, the hydrochlorofluorocarbons, the methanes, NOx and SOx, the greenhouse gases that are out there. They would need to be mitigated. And that gets into an entirely new discussion of carbon capture and sequestration, carbon capture utilization and sequestration. And of course, one of the greatest carbon capture and sequestration projects is called a tree. And there is a Trillion Trees program, which President Trump signed up the US for or supported in some form or fashion. And this is well on its way now to plant 1 trillion trees around the planet to take carbon out of the atmosphere.
I have a question.
I have a question too.
So
Go ahead, Lawrence.
there, for like 110, 120 years now, we have developed a tolerance for the explosiveness, the hazards of gasoline. We have learned how to deal with it. We've learned to accept it when we can't deal with it. What efforts or what technologies are being developed when we get energy density that's similar to gasoline? I feel that we're going to have the potential for explosions and fires that are also similar. What is being done to ameliorate that?
It's a great question, Lawrence. Within the industry, there is a tremendous amount of work effort being applied to this. As you might imagine, no one who develops, manufactures, and sells a product wants to hear from their customer that it blew up on them. So let's step back to a basic element here. All of the lithium-ion chemistries which are in common use today, lithium, nickel, manganese, cobalt oxide, lithium iron phosphate, and lithium titanate oxide, along with nickel, cobalt, aluminum oxide. All of these chemistries bring their own oxygen along with them. So as everyone knows, you need three things for a fire. You need fuel, oxygen, and a source of ignition. Well, within a battery, within a cell, within a battery, to be more explicitly correct, all of those things are available. A short inside of that cell, because a dendrite has grown from the cathode through the separator to the anode, causing a short, now provides a source of ignition. The fuel is there with electrolyte and other elements within the battery, and the oxygen is there. And so that oxygen then feeds the fire. And what happens commonly is that you have one cell which has a failure, and it goes critical, and it catches on fire, and it will heat up the next cells adjacent to it. As it heats up those adjacent cells, they will go critical, and you start to develop a cascade failure like that. So this is, I think it's fair to say, well known and well understood within the industry. There are many, many layers of safety that a company like mine, for example, would build into a battery energy storage system. I think you could probably count about 7 or 8 layers. And that starts with the cell. So the cell that you select, each of these cell chemistries has a different preponderance of being thermally being thermally active. Okay, so an LFP cell is more safe than an NMC cell, and an LTO cell is safer still, and an NCA cell is less safe. So cell selection is part of that. And then you have module design. So you can do certain things within the module, including providing a thermal barrier, a break from cell to cell, for example, to slow down that propagation time. Importantly, each module in any battery system has a thermal management system, so you can address the thermal management as part of your catastrophic failure plan. And so that's another way to address it. At the system level design now, there are multiple things that can be done as far as, again, isolating, putting up thermal barriers. There are materials which will absorb a lot of heat and sort of dissipate it innocuously. There are other elements such as gas sensors. So before the cell would catch on fire, the electrolyte would vaporize. There is a pressure relief valve in the cell. There are gas sensors that would detect that. That would cause the system to shut down and perhaps increase the flow through the thermal management system. There are other mechanisms, including fire suppression, that uses different kinds of gas to neutralize the fire or to serve as a thermal absorber so that you don't propagate. One of the rules of thumb is that once a cell goes critical and is on fire, you can't stop it. Okay, you can't put it out. It's just going to burn itself out. What you do want to do is you want to be able to stop the propagation from cell to cell. If you can stop it after one cell, okay, well, you've had a failure, but it wasn't catastrophic. There are numerous elements that go into that. I've touched on some of them. There are more. There are certain materials that will absorb a lot of heat so that it attracts the heat essentially and saves the adjacent cells from receiving all of that heat. And then you have things like water. Okay, well, you can use water on a car fire, and you see it all the time. And then you read that, yes, you know, the electric car caught on fire, the battery was on fire, the fire department came, they put the fire out, and they left, and the car caught on fire again. And they came back and they put the fire out, and the car caught on fire again. And this goes on and on until you get to the root cause. So the water doesn't put the fire out. What it does is it stops the propagation. It's a mitigation element to stop the propagation from cell to cell. So it is a very important issue, very much part of the industry playbook to improve the safety, certainly. There was another question, ma'am?
I have a question. This is Leslie. I'm interested in platforms and standards, and I'm going to give you a metaphor for that. In the PC industry in the mid 80s, the platform and standards were Intel's 8088 chip and Microsoft's operating systems. Those were the platforms and standards on which everything else was built, and that propelled the industry up for quite a while. What are the platforms and standards on which, if there are any, if this metaphor makes any sense, are there any platforms and standards on which the battery industry is built?
That is a wonderful question, and truly a very insightful question. So there's a bunch of answers to that. Let's start with the cells. So there are not a lot of standards around cells. And so I also began in the semiconductor industry working at IBM up in in the Northeast, and then coming down here, and also working with many different semiconductor companies. So in fact, I was the chair of the Texas chapter for some years. Understanding the importance of those standards, it is kind of striking to me that the battery energy storage industry does not have a similar function yet. It is truly more of the Wild West days, is what we called it in the semiconductor industry, right? It's similar here now. There are not very many standards. And as I imagine all know and understand, those standards will allow you to improve Wright's law, improve the economies of scale, improve the efficiencies for everybody across the entire food chain, and reduce costs, and improve efficiencies, improve quality, and will serve as a much better starting place at the cell, the building block for the whole entire battery energy storage system. The industry is not there much. There's a little bit. There is a standard called VDA. It's a German Deutsch standard. Okay, that is a nominal standard that exists as far as cell sizing. I'm not real familiar with it, other than I know that it's sort of out there a little bit. But if you go and you look at 100 different cells from 100 different suppliers, you'll probably find that every single one of them is a different size. And that, of course, is just crazy stupid, right? I mean, what if every, semiconductor wafer was 200, 205, 207, 207.5, I mean, that's just crazy.
Yeah, I wrote software for machines called the Victor 9000.
I think that was a long time ago, if my memory serves.
Yeah, obviously before I was born, but and the day my software was done was the day they declared bankruptcy. But there were so many and that's what in the innovation business we call it the chaotic phase, and you called it the Wild West. I think that's pretty much the same thing. There's a chaotic stage,
right.
And then that's followed by a standards phase, and the industry takes off when everybody sort of goes around a standard, and everybody agrees on a standard.
Right.
So I'm wondering where those standards are, and it sounds like they aren't there yet.
They are not there yet as far as the industry itself, and I have to say it's a problem. There is there are common cells, like say an 18650, okay? And an 18650 means it's 18 millimeters diameter, 65 millimeters tall, a cylindrical cell. I showed a picture several times on the screen today, okay? Now, we make modules using an 18650 cell, but when we change to a different cell supplier, they don't work anymore because we have certain tolerances. The engineering design, the module design is based upon the original cell and the original tolerances. And what you will find, just like in the software, you have this vaporware, okay? And they will play games with the standard. Yes, it's a 21650, but it's actually like 0.5 millimeter in greater diameter, because they want to squeeze a little bit more energy in there, and they want to be able to claim a little bit more energy and play marketing one-upmanships, right?
So they're not compatible.
They're not compatible. And that is, from a manufacturing standpoint, an absolute bane of our existence, that we can't just use, I'm thinking about, like SEMI M1, for example, the material standard for wafers. Yeah, I know exactly what I'm going to get, and I know exactly what the tolerances are going to be on that, and I can buy wafers from anybody, and I'm good. I can't do that in the battery storage business today. I have absolutely no doubt that this is coming. It's just logic, right? The solar industry has migrated to standards. The battery industry will. Now, it's not to say that there aren't certain standards for other components. So, maybe there are standards having to do with transporting these cells. Okay, so there are safety standards with that. There's standards regarding the modules performance and safety standards related to that. There's safety standards related to the systems. And these would be IEC standards, UL standards. I think there's some NFPA, maybe some NEC. There's a number of governing bodies who have presented, forwarded certain standards. Some of them probably have more buy-in from the industry than others, but certainly the industry, I suppose I can speak for it at some level. The industry understands, respects, and appreciates that standards are important. They're there for good reason, and they serve everyone's interest, but we need to get past the Wild West stage first, Leslie.
Yeah, well, you talked about standards bodies, and sometimes standards bodies like IEEE will take precedence, and sometimes it's just a de facto standard driven by industry companies. For example, no one would ever have claimed that Microsoft DOS was the best operating system, but it became the standard.
Right,
And
right.
and so the same may be true in battery technology. Something may become the standard, even though it's suboptimal.
The ones in my experience, and I saw the first color television at Sarnoff Laboratories when I was 13. And RCA drove the National Television Standardization Committee. There was a dominant player that made it happen. And the same can be said for Intel and the Microsoft. And by the way, there was also an Apple and a 6502 and some games that came up through that way. But it's rare that we get a committee of people involved in the industry that sit together at a table and decide how the standards are going to be. They are inevitably set by a dominant player. So what I want to know is, so who's going to be this? Who knows? Maybe it's Tesla, maybe it's somebody else, but there's going to be a dominant player that does things a certain way, and then everyone else adheres to that.
Right, and historically, and I'm talking about thousands of years historically, the standard is set when there's a military need and an application that has to do with a military need. And for example, the standard for telegraph systems was driven by Britain's need to control its far-flung empire and find out when it needed to replenish supplies to Australia.
Right.
Took a long time to find out if you didn't know it.
NTSC was not that way, and Europe didn't adopt the NTSC standard. In fact, the French called it never the same color twice. Never twice the same color.
Let me see if
French
I can.
had this CCAM thing, which we derided as surely everything contrary to American.
Okay, well, let me go on ahead and answer some of the other questions here, so we can,
Thank you, Tom.
move forward. You're very welcome, Leslie, and that was a brilliant question, extremely salient point. Tom Starnes says a gasoline engine, ICE, will take care of all these problems except maybe for powering your phone directly. Well, I don't know, my car powers my phone now, so that one's covered, I think. Could be converted to natural gas or propane if you want to be cleaner, cheap, and today not a lot of future wizardry promised. So one of the things I've come to really appreciate is, yes, you can do it. Yes, you can make a natural gas car using a fuel cell, for example, or just a natural gas turbine. You can use propane. There's all kinds of fuels. 150 years ago, we had electric cars, we had wood-fired, steam-powered cars, we had gasoline-powered cars. At a certain level, that doesn't really matter. And when I was in the product development business for 25 years, I learned a very important differentiation between, yes, you can do it, but does it make sense? Is it economically viable to do it? And are you going to check off all the boxes as far as the ability to scale? And so scale in all of this discussion, I went over and over it with Wright's Law, is a absolutely key component of this. So the fact that the industry is scaling today enormously, investing inordinate amounts of money into the scaling of both the cell production and the electric vehicles themselves. Every single car manufacturer in the world now that I'm aware of, including Rolls-Royce, who is surprising to me, leading many other more better known competitors in that race, are coming out with their own electric vehicles. So it is the ability to scale. Even if we wanted to make a natural gas car, a propane car in California, you can buy a fuel cell vehicle and you can go to a natural gas station and fill it up. But they've not caught on, and I don't expect that they ever will because of the economies of scale. So that would be my suggestion for that one. Bob Ascott writes, I guess I don't understand the benefit of a car with its battery to the big picture of the grid. The car is storing energy for my next trip. How does this help the grid? Great question. This whole idea, the big idea that I hope to be leaving you with, is the idea of a virtual power plant. The implications of this are far broader than I understand, and I've been thinking about it for quite a while, and certainly far more than I can explain. But let me try it this way. The average American drives their car less than 30 miles a day. If you have a Tesla with a 400-mile range and you need 30 miles a day, how many of those remaining 370 miles are you willing to sell to the utility if the price is right, in order to be able to, one, arbitrage the industry and make some money, two, trade that off with some virtual power purchase agreement provider and organizer like a Tesla auto bidder, and they will sell you, I'm going to make up numbers here, they will sell you a Tesla Model S for $25,000. But you sign up to let them tap your battery, so they will buy and sell energy 100 times a day, and you don't even know it. It's going on in the background. And they're gonna lease the battery to you, so you don't have to worry about that. So you can take that worry off your worry list. Now the car is able to serve all of your transportation functions. And let's just say that normally you drive 30 miles and you say, well, I got 370 left. I might need to go to the store and, visit my friends. So you can take 300 miles of range out of my car. So you tell the VPPA company, go ahead and take 300 miles. Well, if you want to drive to Dallas tomorrow, you probably want to remember to not have them take out the 300 miles, okay? Because otherwise you're going to go out in the morning and oops, there was a cold snap overnight, and the coal plants and, the natural gas plants and the wind turbines. Of course, everybody in Texas knows those wind turbines are the problem and they cause cancer. So, sorry. The ability to go anytime you like is important. That's an important component of this. So let's just say you're going to drive to Dallas and you forgot to tell them about your need. Well, you go out to the car and there's only 100 miles left, not the 400 because they took 300 out. Well, you can go to a rapid charging station and get about 80% of your range back in about 10 to 15 minutes. And that may be a little bit optimistic for today, but that's sort of very near term, right? So one of the really important high level components of this, which I haven't touched on, is back on that energy graph that I showed multiple times. Up in the top center, there was the electric generation component, right? Well, that electric generation component, people say, well, you're going to take all of this big lump out of petroleum, you're going to have to put it into electrical, and you're going to need to put 35% of our US energy into the electrical grid. And my answer is no, I don't believe that, because with a virtual power plant, what you can do is you can take all of that wind from West Texas that we literally throw on the ground every single night. We throw it away. There are plenty of places in this great state where you can get electrical power for free after 9 p.m., for example. All that energy is going to waste. If they put that energy into your car and you sold it back at 3 in the afternoon, now you have a much more efficient system, okay? And you're able to monetize that, capitalize on it, have a much more efficient system, just, you know, an electric vehicle to a gas vehicle, but you also have a much more system at the holistic, you know, top level where you, you're able to manage this. It'll take, you know, a lot of computing, a lot of electrical engineering, a lot of software engineering, but you will have a much more efficient system. And I have seen reports discussing how we won't actually need to increase our capacity on the grid at all, which is interesting, because all of the capacity that we need is targeted towards our worst case production demands. The demand charge on your electric bill goes to what is your worst case demand for electrical power, and the whole system is built on that. The rest of the time, the system's running inefficiently. Well, if you can take that inefficiency, stick it into something useful like your electric vehicle or your home energy system, then you start to see extraordinary efficiencies come out of the system and huge benefits. Does that help, Bob? Okay, excellent. All right, so let's see. And Kai, I honestly don't know what time we're supposed to shut down here. I'm going to keep going if people are still asking questions and listening. Tom Starnes says, you haven't said anything about efficiency of charging and discharging batteries and what the losses are, and is that going to get any better? I'm not positive that I remember the round trip efficiencies. Joel doesn't look like he's online anymore. My recollection is it's about a 90% round trip efficiency. So whether you charge or discharge a battery, you lose energy to heat. And depending upon the rate that you charge the battery, you will lose more or less heat. So if you have to charge it really fast, you're going to lose more energy. It won't be as efficient, but if you can charge it more slowly and gently, you will be more efficient and have a more efficient, you know, round trip efficiency curve on that. Now, is it going to get better? Yes, absolutely. I touched very briefly on solid state batteries. And so solid state batteries are more efficient. Well, they're significantly beneficial in so many ways, not the least of which is that they can be charged faster and they generate less heat, so they have less losses, so they are able to have a better round trip efficiency. So maybe that's the answer to that one. Mr. Harris writes, will Tesla's 4680 standard become a standard? So going back to Leslie's questions about standard and my discussion of 18650s, 4680 is not a standard unless you are Tesla, okay? Now, part of the reason that you didn't have a 4680, and that means 46 millimeters in diameter, 80 millimeters in height. The reason you didn't have a cell this big till now is because you didn't have what was called the tabless design that Tesla has developed. That allows them to take heat out of the battery more efficiently, and it allows them to have a higher current flow because you've got more contact surface for the conductor itself in the anode and cathode to the battery contacts. And so will it become a standard? It'd be pure speculation on my part. Tesla has, I'm sure, it tied up pretty well. I actually have the patent here for the 46, well, it's not for the 4680 as much as it is for the tabless design. So they have intellectual property on this. Joel Sandal's company has intellectual property on this. Depending upon how that could be worked around and other cell manufacturers pursue that, I don't know that you could make it a standard, because once you get that large, you have these other challenges I mentioned, and you need a solution. The tabless design is the solution for that. Lawrence Reagan asks, as for costs of EV versus gasoline powered costs, it appears to me that the EV cost will be much lower once the learning takes place and competitors get in the game for sure, since the number of components and the labor to install them is dramatically smaller. I absolutely agree, Lawrence. In fact, just within the last couple of days, I saw some trade press about that, indicating about a 30% improvement in labor content in the car, and similar numbers in that range as far as the bill of material costs. It's just a lot simpler. So yes, the costs will go down, and that will drive up the volume sort of automatically. Gray Abbott says sold, and Lawrence has left. And Mr. Harris says vehicle to grid means no need of peaker plants. And I would agree with that. I certainly think we're a good ways away from taking our gas peakers offline. I'd want to keep them around for a while until we have them collecting dust in the corner for quite a few years, but I would agree with that. Okay, any other questions from anyone?
Tom, James Mercer.
James Mercer, how are you, old friend? So good to see you.
Thank you. Good seeing you too. I just wanted to ask you at this point, I think it kind of fits in. Tell the story about the mining company in South America that bought your batteries for their trucks, and they only charged them once from the external source and never had to charge them again.
Okay, so I may have been a little bit overdone with my story when I told you about that, James. The story was true except for the word "our." Okay, those were not our batteries in that vehicle. There is a mine in South America high up on a hill. It's an open pit mine, and it has some of these very large Terex Titan type trucks that are very large carrying capacity. And the mine is at the top of the hill, and the trucks go down to the bottom. When the truck was delivered, the battery was charged, and it went up the hill. It picked up its load, and it came back down the hill in a low gear, going slowly. It had so much regenerative energy, it was able to recharge the batteries on the way down with the full load, that it could drive all the way back up with the empty load. And so the battery was charged one time by the operator, and then forevermore on every cycle by gravity, which from my vantage point is a pretty darn good deal.
Yeah.
Okay, anyone else? Okay.
All right, so it's almost 8 o'clock. If there's no more questions, let's give Tom a hand. Very, very interesting topic, and I learned a lot. And let's stop here. Okay, thank you.
Very good. Thank you so much.
All right, good night, everybody.
Okay, good night, everybody.